This is number 2 from the last minute review, so let me read through the problem here. A sand pit is being filled with sand whose height at any time is given by a differentiable function, h of t, with domain of t between 0 and 12 minutes. H prime is a differentiable function representing the rate. Let me see. H prime is a differentiable function representing the rate at which the height of the sand pit grows in inches per minute. It is known that H prime is increasing on its entire domain, so this H prime graph is always rising. We see it here, and we see that the graph is everything between is going to be increasing as well. Values of H prime are given at select values in the table above. The height of the sand pile is 40 inches. At t equals 9 minutes, so h of 9 is equal to 40. We don't have h of t in front of us, but they just give us this information for use later on. All right, estimate h double prime of 2. With units, explain the meaning of h double prime of 2 in the context of this problem. So h double prime is going to be the derivative of h prime. But obviously we don't have a function of a formula for us to find the derivative to get from h prime to h double prime. So the best that we can do is understand that h double prime is really the rate of change of h prime. So let's just go through algebraic method of slope. All right, change in h prime over change in t will give us our estimated h double prime of 2. So the slope at 2 is going to be best approximated using the closest t values, so between 1 and 3. So now we can do h prime of 3 minus h prime of 1 over 3 minus 1. Now h prime of 3 is going to be 5. H prime of 1 is going to be 2. So change in y over change in t, or change in y over change in x. 5 minus 2 over 3 minus 1, we get 3 over 2. And our units of measure is going to be inches per minute squared, right? This is inches per minute, so anything that is a rate of change of inches per minute is going to then turn into inches per minute squared. All right, explain the meaning of h double prime of 2. Now, h double prime of 2 is talking about the whether the rate is increasing or not, right? And here we're getting a positive value, so this tells us that the rate at which the sand pit height is increasing, or basically the rate of the sand pit height, which is represented as h prime, is increasing. So the rate is increasing, okay, not the height that's increasing, it's the rate that's increasing at 3/2 inches per minute squared at t equals 2 minutes. Okay, so the second derivative is always going to be describing the rate of change of the first derivative. All right, part B, write Riemann sum with the subintervals given in the table to approximate the definite integral from 0 to 12 of h prime. Okay. With the units, explain the meaning definite integral from 0 to 12 of h prime of t in the context of this problem. So the definite integral from 0 to 12 of h prime, we're going to split this up into intervals here. So I'm going to split this up here, and we can subtract the t values to get the width, because we're just doing width times height. All right, Riemann sum, we're dealing with rectangles. So 1 minus 0 is 1, 3 minus 1 is 2, 9 minus 3 is 6, 12 minus 9 is 3. So now we want to find the appropriate height. We want to write Riemann sum. So what that means is we're going to choose the height on the right for each of the subintervals. So that means for the first subinterval here, we're going to choose the h prime of t on the right side, so 1 times 2. Second subinterval has a width of 2, height of 5, then 6 times 7, and then 3 times 10. We combine all those together, and we get 84 inches. Now, when we do antiderivative, our h prime units are going to change. right? So inches per minute is all of a sudden going to turn into total inches because we've accumulated those rates over the course of the time period. So this tells us that between 0 and 12 minutes, 84 inches of sand has been added to the sand pit. So the height has changed from or over the course of the 12 minutes, the height has increased to up 84 inches. Okay, so that's what this 84 tells us. All right, including units, evaluate the depth integral from 0 to 9 of h double prime of t. Notice that we don't have any h double prime for us to find the area of. So we're going to have to rely on something else. What we can do is maybe we can convert this into h prime and then use our h prime table instead. Well, to get from h double prime to h prime, we can make it, since we're making it go through antiderivative step process, then we're really going to be applying first theorem, right? First theorem says the antiderivative of a function is going to turn it into its antiderivative. So the antiderivative of h double prime is going to be h prime. So h double prime is going to turn through this process into h prime, and then we plug in our upper bound minus lower bound. So this turns into h prime of 9 minus h prime of 0. And now we can use our table here. H prime of 9 is 7, and then h prime of 0 is 1, so 9 minus 1. I'm sorry, h prime of 9 is 7, so 7 minus 1 is going to be 6. Okay, part E. Write the equation of the tangent to the graph of h of t at t equals 9. So that means we want to, let me finish reading this here. Use this tangent line to approximate h of 10. Is this an over approximation or under approximation of the true value of h of 10? Okay, justify. So we need, if we want to find the tangent line equation, we need order pair and we need slope. The order pair is given to us here. H of 9 is equal to 40. So that information is provided to us at the beginning of the problem. And then h prime of 9, right, that's the slope that we need at that point. H prime of 9, we can look at our table of values. H prime of 9 is going to be 7. So we have our order pair, we have our slope. So we're basically going to put into point-slope form. But instead of y minus y1 equals m times x minus x1, I'm going to use t and h since those are the variables that we see here. So h minus h1 is equal to m times t minus t1. I can plug in my order pair, 9 in for t, 40 in for h, and then I can plug in my slope, which is 7. And now I can just add that 40 to solve for h. And once I have h equation in front of me, now I can use this to approximate h of 10. So I'm going to plug 10 in for t. And this will give me 7 times 1, which is 7, plus 40, which is 47. So we have a linear approximation using this tangent line at t equals 9 to approximate the value of h of 10. Now it's asking whether this approximation is going to be over approximation or under approximation of the actual h of 10, because we know that this is just an approximation. This is not the exact value. So how can we make that determination? Well, we do know that h prime is increasing over that interval. So if h prime is always increasing, that is telling us that basically this is going to be concave up, right? If my derivative graph is increasing, that translates to be concave up, a second derivative value that is positive. So if my h prime is always increasing, then I know that there must be part of a concave up graph. If my graph is part of a concave up shape, then any linear graph, any line that is skimming the surface of that tangent line is going to be under my graph, under my curve. So anything that's below my curve, that means any approximation that I use on this line, which we use to find this value of 47, it must sit below the curve. It must be an under approximation. So because h prime is always increasing, we have a concave up graph, and if we have a concave up graph, linear approximation is always going to under approximate. All right, explain why there must be a value c on the t interval from 9 to 12 such that h prime of c is equal to 8. So this is the h prime graph. Can we guarantee that this h prime graph is going to reach h prime value of 8? Well, we know that the graph is going to connect between all these points because they say h prime is differentiable, which must mean that it's also continuous. So really, if we want to guarantee h prime of 8, we just need a value that is lower and a value that's higher. So if h prime is going to go through 7 and all the way to 10, then it has to reach 8 somewhere in between. What we can use is IVT. So intermediate value theorem says if we want to guarantee a specific y value, we just have to make sure that one end has a y value that's below and the other end has a y value that's above. And we do see that in this case. So just to be able to justify it in a statement, we can say since h prime is continuous, it says differentiable, but we're just going to state the fact that the continuity is what's key here. So because h prime is continuous, that means there's no breaks, then by IVT we can guarantee h prime of 8 on the interval from 9 to 12, because on one end we have h prime of 9, which is less than 8, and then on the other end we have h prime of 12, which is greater than 8. So if we go from a value that's less than 8 and then arrive at a value that's greater than 8, then it has to cross through 8 at some point in time. So there must be a c value where h prime of c is equal to 8. All right, our last part G here. Explain why there must be a value on the t interval from 0 to 12 such that h double prime of c is equal to 3/4. Now this is applying mean value theorem. We're trying to guarantee a specific slope off of this h prime graph. And if we want to guarantee a specific slope, then we can use mean value theorem and see if the slope between the endpoints produces 3/4, because if it does, then we can guarantee a slope of 3/4 for this h double prime. So let's look at our endpoints, 0 and 12. So we're going to adapt mean value theorem one derivative down. So we can adapt it by saying, well, h double prime of c, we can guarantee a slope of for h double prime if h prime of b minus h prime of a over b minus a gives that slope value. So let's test it out. Well, our a and b values are 0 and 12. So we'll do h prime of 12 minus h prime of 0 over 12 minus 0. And we look at our table of values. H prime of 12 is 10, and then h prime of 0 is 1. So 10 minus 1 over 12, that reduces to be 9/12, which is 3/4. And because there's a slope of 3/4 that sits between h prime of 0 and h prime of 12, then we can guarantee that there must be an h double prime of c that's equal to 3/4. Okay, therefore there exists a c value on the time interval from 0 to 12 such that h double prime of c is equal to 3/4.